In the last video, we learned that if we plot the position of an object as a function of time, the slope of that plot gives us the velocity of the object. In this video, we're going to use that result to obtain a formula which will allow us to start solving our first kinematics problems. Let's say we have a person running along the x-axis with a constant velocity. What that means is that they are not getting faster or slower, and they are not changing their direction of motion. At time 0, the position of this person is x0. At time 1, the position of this person is x1. So what we're going to do is plot the position of this person as a function of time, starting at time 0, ending at time 1. It's not going to be a super quantitative plot, but really just a sketch to give us an idea of what's going on. Okay, so we're plotting position as a function of time, which means position on the vertical axis, time on the horizontal axis. And we're going to plot the motion from time 0 to time 1. Now, according to what we have in the figure here, at time 0, the position is x0. So let's find that point in the plot. Okay, so this point here represents the position of that person at time 0. Okay, then according to this plot, we have that at a time t1, the position is x1. So let's find that point in the plot. Okay, so this point right here represents the position of the person at time 1. If that person is running with a constant velocity all the way from time 0 to time 1, then the slope of that position versus time graph will be a straight line. And now let's find the slope of this plot using rise over run. So I'm going to draw a slope triangle. Right, now the horizontal leg of the slope triangle represents the change in time, and that would be the difference between this time and this time, namely t1 minus t0. And then the vertical leg of the slope triangle represents the change in position, which would be this position minus this position, so x1 minus x0. And as we discussed before, the velocity is the slope of the position versus time plot. So coming back to here, we can say that the velocity is rise over run. Now, the rise would be delta x, and the run would be delta t. So here we have one equation that we can use to describe situations where an object is moving with constant velocity. If an object is moving with constant velocity, then that velocity is equal to the change in position divided by the time interval during which that change in position occurred. Now we can get another formula. So for that, let's go back to this equation here and replace the delta x with x1 minus x0 and the delta t with t1 minus t0. Now we're going to do a bit of algebraic rearrangement. So let me take that t1 minus t0 up to the left. So now I have v times t1 minus t0 equals x1 minus x0. Now I'm going to take that minus x0, move it to the left, and then switch the sides of the equation, which gives me x1 equals x0 plus v times t1 minus t0. Okay, so these two boxed equations are mathematically equivalent, but the second one gives you kind of a different perspective. The second equation gives you the final position of the object in terms of the initial position and the time interval. Both of these equations here, again, they are mathematically equivalent, and they are valid only when we are describing an object moving with a constant velocity. In the next video, we are going to begin using these equations to solve some kinematics problems involving objects moving with constant velocity.